All right, so Python review. So Python is an interpreted language designed to be easy, readable, and powerful. So, oopsie. By readable, we mean that you can look at the script and easily understand it, right? So it should be very easy to come to a script that you're not familiar with, and if it is well written, then you can easily look at it and figure out what it's doing, right? This is in contrast to a language like Perl. Perl is an older system scripting language that Python has largely but not entirely replaced, and there used to be a joke about write-only Perl. And the reason for that is that Perl used these sort of arcane $_ underscore, at $, tokens to mean very specific things, and it was not easy to figure out if you were not familiar with Perl, or even if you were coming back to a script after time had passed, to look at it and go, at $_ underscore, what the hell is that, right? Python does not do that. Python uses these very easy, very explicit, very readable, sort of like English language descriptions, right, that make it fairly easy to figure out at a glance what it's going to do, right? 4x in these numbers. Even if you're not familiar with Python, you could probably guess what's about to happen, right? You're going to iterate over this list, and everything in it will be assigned to x in turn, right? So by powerful, we mean that a lot of work can be achieved with relatively few very powerful, very effective symbols and keywords, right? So again, if we consider our for loop, okay, let me think this through again, right? So if we consider our for loop, right, we might not think about it, but a fair amount of work is actually occurring automatically and implicitly to make this happen. So there are other languages where you actually have to look at a lot of that work, right? So like if you're used to Java or C, then you have to create like a counter variable, right? You'd have like for I oh, and I'm embarrassing myself because I have forgotten the syntax. Good Lord. Brain's having trouble shifting gears. Let's just say 10. Right? So you have to, in order to iterate over an array, explicitly keep track of your own pointer variable, and you have to explicitly get this length right? So maybe I got this number 10 from somewhere, or maybe it's an error and I'm wrong and my code's not going to work, right? So C++ also has iterators. So the standard vector can yield an iterator, and then you can use iterator-based iteration through this loop, or through this container, but it's worse. You have to keep track of this typed thing. And it's a huge pain, right? So it really is kind of nice that for an iterable object, of which list is 1, Python is just going to let us write 4x in our list, and we don't have to worry about any of that. We're getting it right. It's just going to yield everything from list into x for us, right? Very readable. We can look at it immediately and know what it's doing. Very powerful. It's going to take care of all of the potentially subtle work, right? Because if this is a list, maybe that's easy, but if this is some other construct, maybe it's having to do work to iterate over it, right? So if you do for line in file, or I guess it would be file.readline, right? then this is actually probably yielding a generator, and we're stepping through the generator, but you as a programmer don't have to care about that. Python will just naturally make all of this stuff line up. However, we pay a price for all of this, and that is that Python is slow. It is very slow. I have seen the number like factor of 100 times slower than analogous C code thrown around. Some of that is just inescapable because it's interpreted. Some of that has to do with the way Python's type system works. So Python uses a notion of duck typing. And that basically means that Python objects have, when you try to dispatch a method on them, the interpreter has to search through potentially a large chunk of an inheritance tree. And that just becomes extremely slow, right? So you might ask, wait a minute, if Python is so incredibly slow, why are we going to be using Python to do a bunch of computationally expensive machine learning? Well, that's where NumPy and TensorFlow are going to come in. We'll meet those in a bit. So, basic syntax. Not going to go over this in detail. I'm hoping that most of this is stuff you've already seen, right? So I've got here a little basic script. Because Python is interpreted, right, I could put this into a file. This script creates a list object, assigns it to the variable numbers, creates this little int object, assigns it to the variable product, and then, it multiplies product by everything in this list. So what we're doing is we're just building up all of this list multiplied together, right? It starts out at 1, and then we multiply it by 1, then 2, then 3, then 4. And the thing that we get is all of these things multiplied together. And then we're printing it. And you guys might not have seen this before. So the F format string, that's new in Python 3.6 or 3.7. It is not particularly tricky. That's part of why I feel comfortable sort of introducing you to it. Hopefully, like a lot of things in Python, even though it might be novel, it should be obvious enough what it does that it won't, so you can just kind of guess how it's going to work, right? So, because this F prefix is here, the interpreter is going to intercept this pattern, this bracket, prod bracket, and replace it with the value of prod, right? So what is not going to be printed is product was bracket, prod bracket. What is going to get printed is product was whatever this is, 24, right? And you can see that down here, right? So I can run a program run a Python script. I'm going to often call them scripts, right? Because these are often called scripting languages, even though they really can be like full-featured, sophisticated programs, right? Do not infer from me calling it a script that I'm implying any limitation of the capability or scope or sophistication of the programs we're writing. But anyway, I can run my Python script by invoking the interpreter on it, which is what I'm doing here, right? Python 3, my script, and then it's going to do all of this, which produces, you can't see the pointer. It's going to do all of this, which is going to produce no output, and then this line will write output, and that's what we see at the bottom, right? And in fact, I have this ready, and a bunch of junk in the way. So this is a Linux terminal. I'm hoping that nothing I'm going to do is shocking or confusing because this is not a Linux class. Here is my Python script, right? You can see pyrefresh.py. If we look inside it, it is the code I was just looking at. Cat just dumps the contents of a file to the terminal, right? So if I call the interpreter on that, then it interprets it, and when it hits the print line, it prints out like product was 24, right? So just to be clear, whoopsie, I already have a Vim running somewhere. There it is, by Vim. All right, so just to be clear, if I were to comment this out, hash or pound is the Python comment character, and save it, we all know what's going to happen, right? So if I were in class, I would make you answer me, but we're not physically in class, so I'm just going to kill a minute of time while you meditate on this. If you have an answer, right? Nothing. Well, nothing is not precisely correct because it does actually run all of these instructions. It's just without that output, we never see the result of the computation, right? It computes that product, and then the script ends, and everything is discarded, including that result. Okay. So, because Python is an interpreted language, because it's sort of oriented toward, because the interpreter is designed to read sort of instructions like written in plain text in a file, we can also just call it, right? So instead of python3.pyrefresh, I can just type python3, right? And now I'm looking at an interpreter where I can enter the same kind of instructions. Oh, sure. So if I just do that, it's not going to work, right? It's going to print X. What I actually want to do is put that in the brackets. There we go. See? So you might notice, I mean, this works. This clearly works. It has a couple of awkward behaviors, right? So notice that when I hit that enter, it doesn't tab over for me, which some nicer editors will automatically do. I have to tab for it, right? Notice also that it didn't remember all of this code as a block. It's doing it line by line by line. So I'm hitting up and down to go through the scroll back, but the scroll back is, as we might say, line-wise. So basically, trying to do a lot of interactive exploration at the Python terminal is a little bit awkward. Fortunately, we have an improved terminal, an improved Python interpreter that is designed to be interactive, that we're going to be using quite a bit, and that is IPython. So IPython is also an interactive interpreter, and it is also obviously a Python interpreter, right? So I can also write for x in a bunch of numbers. Oops. There we go. See? But this has a bunch of nicer behaviors, right? We notice that it's doing syntax coloring for me. We notice that it tabbed in automatically for me. We notice that if I hit up, it remembers that whole block of code, so I don't have to start again. We notice that, again, it tabbed over, right? Instead of executing, I get to keep writing instructions here. And if I want to know what x squared is, I can print that too. Convenient. So, and of course, like this, the thing that so right now, the interpreter state obeys all of the usual Python rules for scope, which that might sound fairly arcane. What I mean by that is that x is still in scope. See? The fact that we can kind of run our code and then still have an interactive environment to explore the results is going to be really, really handy. So IPython does have the run command, and let me remind myself what that script's name is. It does have a run command, which I can use to run our script, right? And we didn't see any output because I commented that line out. I'm going to suspend IPython, uncomment that line, and then get IPython back. And if you don't know what I just did, don't worry about it. I just used some Unix job control stuff that is not the point of this class, and I don't expect you to know. To not have to kill and reopen a bunch of stuff. So I've changed my file, and I can use the %run pyrefresh. There we go. But this is convenient because, again, all of sort of the variables from that script are still available, right? So I can look at what x was. And I wonder if cat works. Probably not. I don't know. Oh, it does. All right. So we can see that script, right? And prod should still be around. Yep, prod is around. Okay? So for this fairly trivial script, this might not seem very useful, but for very large and very complicated scripts, the ability to sort of, again, still have an interpreter where you can kind of play around after the script is done and see what state it's in could potentially end up being very, very useful. All right? Okay. Oh, hell. All right. So for reasons I don't understand, it constantly decides it's going to record at a desktop instead of the slideshow. I really hope it wasn't doing that before and I don't have to re-record all those slides. Anyway, so Python is object-oriented. It is very, very object-oriented. In fact, everything is an object, and we do mean everything, right? So before, when I referred to, for example, the variable product as a variable that pointed to an int object, I was not kidding, right? So if we do type prod, okay, float. Oh, because I initialized it to 1.0. All right, I'm dumb. So yeah, if I do type 1, we're going to get int, right? So really everything is an object. If I do def square x, I've got this square function that squares numbers, right? We all should recognize the syntax for declaring. Why is it not drawing? Why aren't you? Why? Oh no. Come on now. There we go. So we should all recognize the syntax for declaring functions, right? But, right, what if I don't type square and then an argument, right? What if I just type the name? It's a function. It is a function object, right? Your functions are objects. So again, in fact, everything in Python winds up being an object. So Python does have a notion of inheritance, but it doesn't have the strong notion of type that, for example, Java has. Again, without going into it in great depth, Python uses the notion of duck typing, right? And it doesn't have the concept of private, right? Which means that Python does not really support a lot of these sort of strong software contract enforcing elements that if you're a Java programmer you might be used to. And sometimes when I teach the Python course at GSU, reliably there is at least one Java person with maybe some industry experience who finds the fact that you don't specify a type, you can't enforce a type, and there's no private just really totally wigs out. I somewhat often get yelled at that moment. Like, they just kind of can't believe that. Yeah, so even though everything is an object, it has a very flexible definition of type. All right. So here in a file, I am declaring, I'm importing sys just to do it. Sys is the system class. It is where, for example, sys.stdout lives. And then I'm declaring a class called clicker. Clicker is basically, it's supposed to be like kind of like a ticket clicker, right? Somebody at like a concert, say, is counting off how many people come in. So basically all it supports is starting at 0 and then counting up. So we have init. Init is kind of like a constructor if you're used to constructors in C++ and Java. I say kind of, the analogy is not really, really perfect. Because there is also a new, but we don't care about that right now. Whee! So this is basically like a constructor that declares an underscore clicks and initializes it to 0. So notice that underscore. Well, okay, so notice the underscore. That is sort of loosely private. So this variable is still visible by everybody as ._clicks. So someone outside of a clicker object could still alter clicks, right? So if you did something like this, you could then do whatever you wanted to clicks. It's not really private. Single underscore is sort of private by convention. If you are a developer and you see a single underscore class, or a single underscore variable name, what that means is the person who wrote this code was telling you, don't mess with this. I have some expectation of what values are going to be in here. I need to maintain some class invariant about this thing. And if you change it in a way that breaks those invariants, you will screw up my code. But in Python, the runtime doesn't enforce that. It's just up to you as a client of this clicker object to have the common sense to not do something to this that's going to break it. There is a slightly stronger concept of private that is double underscore. This is still accessible from the outside. What Python is going to do is mangle the name. Oh, I forget what the string that goes in here is, but it's going to input a string, a prefix at the beginning of this name. And if you know what the prefix is, you can still get to it. So from outside, you could still write C dot, double underscore, whatever that prefix is, and I forget. Yep, that's a word. Right? You just have this extra step of knowing this prefix. And so if this is so if single underscore is suggestion of private, double underscore is strong suggestion of private, is no, really, don't mess with this, right? So this is please don't break my code by messing with this. The double underscore is really don't break my code by messing with this. Oh Lord, there we go. All right. My fun screen drawing program has a lot of different shortcuts, and I only know some of them. So notice also that I explicitly referenced the self object. So the explicit self object gets passed as an argument, and then I explicitly write self._clicks. Notice also that I didn't have to define the layout of the self object, right? These self objects work exactly like any other Python scope works, right? In that, variables are created when they are assigned to, and they do not have to be declared, right? So basically, this is sort of like a Java constructor, where like a Java class that has an int for the click count might initialize it to 0, except I don't have to declare that beforehand, right? I don't have to formally declare that the only member of this class is exactly the clicks object. So down here I've got some functions. Reset, in a fairly straightforward way, just resets the clicks to 0. Click. So again, that's like you're working the gate at, I don't know, a carnival, and you click the clicker, right? So it increments the count by 1, and then get clicks just returns that click count. And if you remember that self_clicks is not really private, you kind of don't need this function, right? If clients of your code know what this is called, then they can just read that directly, right? So this and then the bracket, and then the quote string, and then the paren is going to work the same as this, if I have room to write it. Right? So this, I hope you can read the horrifying sort of salmon purple that is the default color. This, right, calls the getClicks function, which just returns self._clicks. This just directly accesses self._clicks, which we might assume is safe, right, because it's single underscore and because we're not changing it, right? If it's single underscore private, like suggestion of private, and if we're not going to mutate it, we're not going to do anything to alter it, then it's probably safe for us to read it, to print it, right? And this is sort of worth talking about because you're almost certainly at some point going to see me do something like this. Oops, why is the slide not advancing? There we go. So there we can see some client code, right? So all of this stuff might be in another file that is using our clicker class, right? So given this definition, we might use it with this client code. So here I'm going to create my clicker, I'm going to call it a couple of times, and then just to make use of sys, right? I imported it, I might as well use it. I'm going to write with sys.stdout.write, and there's my getClicks. So stdout.write does not put a line ending at the end, so I have to explicitly put a new line. Printf, that's just print, does, right? With printf, I wouldn't need this thing right here. It would put it there automatically. With stdout.write, I have to remember to do that myself. Why did I put this here? Because there's a trick I'm going to use, very possibly, involving stdout.write to write a progress bar for some of our training code when we finally get to training stuff. And it won't work with print because it needs that new line to not be there. But we will possibly see that later, depending on if I decide to use that code. So then I can reset, I can click again, right, and I can print my click count. So the first time, what am I going to see? Well, the first time I should see 3, right, because I clicked 3 times. Then I reset to 0, then I call click again, oops, and then I should see 1, right? So a sort of software engineering note, which I maybe should hesitate to mention because I haven't done a good job of this, is that you should always have at least one test case for every behavior you expect your code to have, right? So I have all of these specific functions. I am trying to test all of them. I'm doing a very poor job of this. A real professional software engineer would yell at the inadequacy of my test code, right? But at least I'm sort of calling everything. I'm making sure I can count up. I'm making sure I can reset and get the results that I want, right? All right. So we can also extend an object. So here, oh, please tell me. Okay, good. It is recording the presentation still. So here is not what I want you to do. Why do you hate me so much? All right. So, oh, for heaven's sake. Sorry, the joys of doing things live. I'm not going to mess with it anymore. So here, I am extending. So classes can extend other classes, right? And that works sort of conceptually how it works in Java or C++, with the additional wrinkle, right, that because of duck typing, you don't need to maintain that Y is an X relationship a lot of the time, right? Sorry, anyway. So first I'm creating a new exception, the clicker exception, that extends the basic exception. This is a good way to have a special exception just for my class and my code. Notice that I'm using pass here. So we use the pass keyword in times that we don't actually want to have a body for something, right? Excuse me. So when I create the clicker exception, All I want is a different type identity, right? So that this exception will be different to base exceptions when people start trying and catching things. I don't actually need to add any additional behavior to it, so I just say pass. There's no body, there's nothing to do, we just have a new exception type that we can try and catch separately. Then I'm declaring my multi-clicker, which extends my clicker. And so we'll see this in a little bit. In the file where I'm doing this, I actually imported the clicker module. So notice that I have a new init method, and notice that I have called super.init. Unlike Java and C++, in Python, constructors do not automatically backchain. If I want to call the superclass constructor, and I pretty much always do, I have to do it by hand. I have to say specifically, get the superclass, and then call its init method. For this, I really honestly could have probably just left this out. So, I then add this new method. I will inherit all of the old methods from the clicker class. I will add this new method, right, to add clicks, plural. I have a variable count, which is how many clicks to add, and I have defaulted it, right, to none. What this means is that count is now a keyword argument rather than a positional argument. Count now has a default value, okay? So I can omit count. I can do, like C, where C is a clicker object, dot add clicks with no argument here, right? And the interpreter will give count its default value of none and then run the body of the function, right? And so I'm looking at what I get. So if count is none, then I basically do the same thing I would do if you just called click. I increment by 1, right? This is convenient because it means you can just call add clicks like this and it works the same as the click method. It just steps up by 1. However, you can give a number there. And let's erase this very busy screen, right? So again, if C is our object, you could do add clicks 10. And it would then come down here. Oops, that's the wrong one. Okay, so if you did 10, 10 is greater than 1, so it wouldn't raise an exception. It would get down here into this else, and it would add 10 clicks. So notice that I wrote that 10 as a positional argument. I actually didn't have to do that. I also could have written C dot add clicks count equals 10. I don't have to have this count here, right? That's the name. I don't have to have count equals 10. Yay! Different color. But I can choose to if I want to give this a name, right? And this goes all the way back to that readability thing. I can write my code like this, where I write count equals 10, and that way anyone who comes behind me later, which might include future me reading my old code, can immediately go, oh, okay, that's the count he's changing, right? You don't have to look up the signature of this to know what all the arguments could have been. You can immediately look at it and go, oh, all right, that is the count. That is the count of clicks he's doing. In this code, that might have been obvious. When we start to look at TensorFlow, I think it is very fair to say that the TensorFlow API is maybe not the best designed thing in the world. It is a little bit ugly. It's a little bit inconsistent, it's a little bit mysterious, right? And if we have a train function that trains our model that has a bunch of arguments, right? A loss, Oh, I'm blanking on it. The thing that determines the weight update rule. Oh gosh, the update manager whose name I'm thinking of. Right? So like stochastic gradient descent, atom, what's the other ones? Anyway. So if we have a loss, we have the thing that generates the updates, we have a whole bunch of other things, we might have a momentum. It's going to be really convenient to be able to label each of those fields as we go. I probably shouldn't have picked a thing I couldn't remember the call signature for. I apologize for being stupid, right? That will come back, well, that'll help us to come back later and go, oh, okay, right? You don't just have to remember, like, you know, if you see this and then this, right? You don't have to remember that this one is the learning rate and then this one is the momentum if you use this format to label them. So, and the exception, right, the elif count equals -1, just exists so that somewhere, or less than 1, so that somewhere in the refresher you will see if elif else, and you will see how to raise an exception, right? You should already know this, but this is how, this is the if, elif, else construct, and then this is how you raise an exception. All right, so if I can not get completely tongue-tied, I also have this example ready, and this time we're going to use spider. Oh, and it launched, but you couldn't see it because it was on the other monitor. So here is my spider menu. I already have these open. Here is my clicker code. So this is why I explicitly called out IPython. Here is my IPython window over here. I keep forgetting you can't see the mouse pointer. Right? This little thing over here is my IPython window. Right? So here is our clicker class from earlier. Notice a couple of things I've done that I couldn't fit in the slide. So this is a doc string. If you have one string at the beginning of your class or method declaration, then that string will be doc string. The document, well, shouldn't have just done anything right? Will be the doc string, the documentation for your class or object. It is a good habit to get into to always include these things. I, being a lazy academic and not a professional industry person, do not always do that. But I do try to include them at the very least for functions that have any kind of non-obvious behavior, right? Where there could be any confusion about what the function does. Dang it. Okay. Okay. So I have, all of the components I had before, and then another thing that is added is down here, I have this if name equals main construct. So scripts are run from the first line down, right? Which is unlike a C program or Java program which has a discrete main function that is the entry point, right? So you can think of this little block of code as being sort of kind of analogous to a C or Java main function. Modules have a name that goes in this special _name variable. If you are the top level script, your _name is main. So if the interpreter runs this script, it'll first import sys, then it will evaluate this class declaration. And if I called the interpreter on clicker directly, it will get down here and run this comparison. And if I called the interpreter on the clicker script directly, it will have a variable name that is main, and then it will run this code, right? So I can come up here and click run, and we see that it gets run over here. We run my file, okay, and we get 3, so, 3 clicks, and then it prints that, the 3. We reset, we click twice, we print and get 2, right? But again, the convenient thing about IPython is, the environment for our script is still around. So I can type C and get a reference to my object, right? Module name _main, which we already knew. Clicker, that's the type. And I can type, for example, c.click. And of course we see nothing. Sorry, brain glitch for a second, but of course we see nothing because click returns nothing, right? c.click, c.get clicks, right? 4. And it's 4 because this C object is the C object left over from before, right? So we clicked it twice, we printed, and then our script was done, but our C object with its count of 2 was still around, right? And I can do c.reset, and let's click. So again, this is why IPython is useful, right? It lets us sort of experiment with the results of our computation. So I also have this clicker main file. And in this clicker main file, right? Whoopsie. I am importing clicker, right? So this is this. So when I import clicker, the Python interpreter will evaluate this file, right? And when it gets down to that if name equals main thing, it won't run it. It will see, _name will equal, I think, clicker. And then it will not evaluate that code, right? So when we import a module, it gets run kind of the same way as if we just called the interpreter on it, but name is different. All right? So I import clicker as CL. This part is optional, but it's useful so I don't have to type clicker as the full qualified name over and over and over again, which gets tedious. So you could just do from clicker import star, and then you wouldn't have to type CL at all. I do not like to do that because then everything from this clicker file just gets dumped into your current namespace, and that, if you're sloppy about it, can cause name collisions. I like to just give things short names like CL because, typing CL. something is not a hardship, right? And this is normal. People usually, you'll see a lot of places do import TensorFlow as TF. And this gets so common that a lot of places don't tell you they're doing this, and they'll just start writing stuff like, tf.variable. And you're just supposed to know that they implicitly did this beforehand. Anyway, so I import my clicker file as CL. This is where I declare my clicker exception, which again, it doesn't need a body because it doesn't need to have any behavior that a normal exception doesn't have. It just needs to be different. I've got my multi-clicker down here, which extends cl.clicker. I've got a new docstring for my new constructor, and then I've got a short description, a docstring for the addClicks function, which explains what it does, right? And so the addClicks function explicitly mentions the default is none, and if you give it none, it just adds 1 click. So if you omit this, it gets the none value and it just adds 1. All right, and that's the same. And then down here I've got some more code where I create a multi-clicker. I click it, I add clicks with nothing, which should add 1 click. I add clicks with an explicit none, which should add 1. I add clicks 5, which should add 5. And then I add clicks -1, which should cause an exception. So I should add 1, add 5, exception, and I should never get to this last add 5, right? That should be unreachable code. And then I have except clicker exception as CE. So if I get a clicker exception, I'll catch it. If I don't get a clicker exception, I won't. So if some other exception happens, an argument exception, a memory exception, whatever, that will not get caught here. But my custom clicker exception, which I am expecting, will. And then I'm going to print out fail to add clicks with the error message, right? And then I am going to click out. Then I am going to print out what my clicks ended up as being, and that should be 7, right? So again, I can go up here and push the run, and that's going to get run in my IPython console. And I think the first time you do this in a workspace, it will pop up a window, and it will ask you if you want to make a new, I believe it's going to call it a kernel, or just keep the old one. I have kept the old one here. And we get what we expected, right? So we thought that, this line would raise an exception. It was supposed to, and we see that it did, right? And we got that clicks must be greater than or 0, or greater than 0 or none message like we wanted, and then we see click count 7 like we wanted. And again, because this is an IPython console, we still have that multi-clicker. See? Multi-clicker. And we can do stuff like add clicks 5, and then we can look at the clicks variable 12. We can reset it. And these are all methods on the base class clicker that we inherited from, right? Oh, clicks and reset. Ooh, because it's not underscore reset. There we go. And then we can look at the clicks count. And if we want to try that exception handling thing explicitly, we can do c dot add clicks and -1. And bam, attribute error. Oh, shouldn't have been an attribute error. What did I do wrong? Oh, again, underscore. I am so dumb. There we go. There we go. Count must be greater than or 0, and it's a clicker exception. There we go. All right. Again, the joys of doing code quasi-live. Okay. So, food for thought real quick. What did I mean when I said earlier that Python has this notion of duck typing and that it doesn't have a lot of the Java code by contract stuff? Part of what that means, just as a clear example, is that I cannot enforce the type that a user gives as an argument. So a user can do this. Add clicks 50, where it's a string. Right? And the language, so Python has no facility to say this argument has to be an int or a float, reject strings, right? The interpreter will happily take that argument as a string, and it is not going to fail until it reaches, until it reaches this, I think. Yep, that's where it failed. I can tell because this is the line. So it's going to say count is none, or is count none? No, it is not. Then it's going to say is count less than equal to 1, and the string object is not going to have a less than comparison method for ints, right? So less than, greater than comparison, not supported between string and int. So that's what it's going to do. It's going to go here and go, uh-oh, this str thing is missing an argument, or missing a method that I need. It's missing a method for comparing itself to integers. I'm going to fail, right? So what would have worked, I haven't tried this, so I might be allowed to embarrass myself. Let's find out. What I think would have worked is if I had done 2.1 as a float. Yep. So passing a float as an argument is not what we expect, right? Kind of the whole reasoning behind the clicker class is that it represents counts of clicks. Again, like you would use it like a carnival admission thing, right? So it's not possible for part of a person to enter a carnival or a movie theater or a concert, right? But our clicker class allows us to add a fractional number like 2.1. Again, Python doesn't give us the language to express a type constraint here. That really weirds some people out. So why did that work? Because we can, floats can be compared to none with is. So is this float none? No, it's a float. Floats can be compared to ints with less than, so this doesn't happen, right? Is 2.1 less than 1? No. And the fact that 1 is a float and 1 is an int doesn't matter. Can we add a float and an int? So we get down here and we try to add underscore clicks plus equals count. Can we add a float and an int? Yes, we can, right? 2.1 plus 5, where one of these is a float literal and one of these is an int, or a float type and one's an int type. Python supports this, right? It allows you to mix these types and it produces a float output, right? It automatically performs this type promotion. And another thing this implies is that this underscore clicks got changed, right? Self clicks was pointing at an int object, but when this addition, right, returned a float, then suddenly it was pointing at a new float object. But because that float object, right, because it has all of the sort of methods and behaviors we need, the code will just make that replacement and it will keep working, right? So again, not only can I do that, but I can keep calling this, right? So if I do add clicks none, what am I going to get? First off, it worked. And if I get clicks, 3.1, right? So I added a click. So again, So I had that float object that has replaced my old dot clicks, right? Okay, that's maybe poor wording. So I have my dot underscore clicks, which is pointing at a float object that is 2.1. I call this code again with none. What does it do? It goes, okay, is none none? Yep. So it runs this code. So it adds integer plus 1 to the thing that underscore clicks is pointing to. That's this float. Again, float and int addition is supported, so it just does that. Gets 3.1 and then makes the underscore clicks variable point to this new 3.1 floating point object. So again, even though this behavior is maybe not what we expect, this code will keep working. And that is because Python does not have the ability to express a type constraint. As long as the type it ends up with has all of the behaviors that it wants, it will use that type happily and never care if it's getting exactly the behavior you may have thought you wanted or not. All right? So, final question, if I do reset, what is going to happen now? So, let's use the type keyword, or the type statement, to see what c.get or c.clicks is. It's a float, right? Type float. What if I do c.reset? So let's look briefly at what that method is. It does that, right? So again, let's take a second, knowing that this is what that c.reset is going to run. What do you think type c.clicks is going to be now? 3, 2, 1, int. Why is it int? Because that 0 is an integer literal, and now the underscore clicks variable is pointing at that integer type object. That's a little bit confusing. Sorry about that, right? Okay. So another nice thing, whoops. Type I already used a couple of times. We have a couple of other special functions. One of them is dir, which you can give an object. And remember, everything is an object, right? So you can obviously put like that C clicker in there, you can also put a bunch of other stuff that it might not be obvious that it's an object in there. What dir is going to then do is it's going to list all of the names in there. We also have help. Help provides help for an object, which includes yielding the docstring, right? Remember the docstrings that we talked about before? So, if this is our spider environment, I can type dir C and see all the names that C has. Remember, where C is my clicker object. Note that it has defined a whole bunch for me, but I can see that single underscore clicks. I can see it listing the add clicks, click, and get clicks method, right? These are all names defined in that namespace. I can then do help C, and I can get help for that thing, right? Which includes my docstring from before, and it includes information about method resolution order, which, it auto-generated for me, a list of methods, and then their docstrings, right? This is very convenient. So, again, TensorFlow has a somewhat rough API and some kind of shitty documentation. The ability to use dir and help to directly inspect what names are defined on an object, and so what documentation those names have, is sometimes kind of useful. Maybe it shouldn't be. Maybe TensorFlow should have better documentation, but here we are. I am going to go ahead and say, if this seems bad, PyGTK's documentation is worse. The GTK toolkit, at a certain point, I should say the GTK bindings for Python at a certain point didn't have documentation, and the only way you could figure anything out was by prying the objects open with dir and help. These skills are valuable to have. Again, notice when I said, right, we can put anything in there. We can put sys, the namespace we imported, to get all the names in sys, of which there are a bunch. Let's pick one at random. Flags, why not? And then we can do help sys.flags to see if that has a docstring. And lo and behold, it does. Okay? In fact, we can even do dir with no argument, and that will then run in the current namespace. So now we're going to see all of the stuff that is defined in this IPython session, which includes these classes, clicker, clicker exception, and multi-clicker, and it includes these objects that are instances of those classes, right? The C object, the CL object. I don't remember which one CL was. I think that might be from... Oh, there it is. That's the import of clicker. All right. And I guess quit quits, and our sys import. Okay, let's find out what quit is. There we go. Some kind of IPython autocall. Great. Okay. All right, finally, lambdas, right? So earlier I said that functions are objects, right? So it turns out that we also, cat issues, we also have a concise syntax for creating new callable objects. So what I'm trying to do here is I've got this map function. So you give it a list of items, and I have tried to give these things reasonable names, right? So Python, I said earlier that if you read it out loud, it becomes an English language description of what's going to happen. That only really works if you give your variables very easily understandable, readable names, which I really try to do. So items is my list of items. Function is the function to call on each one. What map is supposed to do is you give it a list and a function, and it's going to return a new list that is the result of calling function on every item. You understand? So if I've got my def square x function I can write. Then map 1, 2 square should return the list 1, 4, right? It should call square on everything in the list. It should call square on everything in the list and produce a new list that is the result of that computation. So that's what my function is trying to do. Now, how do I do that? I create a new empty list. I iterate over every item in items, and then I append, right, function called on item. So again, this is sort of functional programming, right? Here, function is my argument, but here I'm calling it as a function on item. And then I'm returning that result list that I have built. So here, I declare numbers, which is this list, and then I have my squared list, which is calling map on numbers, and what's this? Well, that's a lambda. I could have defined, like I said before, def sqr x return x 2, right? And then instead of this lambda, I could have just wrote square, right? And that would have worked. Instead, this lambda keyword is producing a callable object that takes one argument, right? You give it an argument list, and then you give it a single statement, and it yields this statement. So this is basically the same as that def square that I just erased, right? It takes x and produces x squared. And this is going to work, right? This is going to yield a callable object that is going to sort of satisfy all of the behaviors we expect of a function, and so it will work in here, right? So let us see what happens when that code gets run. And where is my Lambda code? I guess I forgot to prepare this demo, so it is map is items function for item and items result.append. Whoops. And notice that Spider is helpfully popping up like autocompletes and prototypes for me, which is quite helpful. Function item. All right, I got to save my code to run it. We'll call it lambda ex.py. Boink. And I've got numbers equals 1, 2, 3, 4, 5, 81, 55.1. Remember duck typing, that's going to work. Because it can be squared. 1. First, let's do it with def square, okay? So I'm going to define a square function for x, and we're going to return x squared. And now, let us squared equals map numbers sqr. Now, did I type everything right? Butterfingers. Yep. So it didn't print anything because I don't have a print statement. But if we look at squared, we see that it worked, right? My new list is the result of applying that sqr function to everything in my old list. And notice also, excuse me again, that it worked on that fractional value without modification. And notice again, right? I never overwrote the first numbers, so it's still there. Well, what if I'd like to map a different function? I could def a new function or just multiply by 2 and then map that. And I think map might be a built-in, so I probably picked a bad name for this, but we don't care about that right now. And that worked, right? So I can just declare new functions like that. That gets a little bit cumbersome. So what if I want to convert all of them to a string, for example? Well, now I can use my lambda, where I provide the lambda keyword, the list of arguments, in this case 1, the semicolon, colon, semicolon, whatever, and then the one statement that it maps to. And in this case, if I want to convert these things to strings, I need strx, right? So there's my lambda, right there. Lambda mapping x to strx. And notice the quotes, right? The quotes are there because now these things are all strings. So if we wanted to convert the number 55.1 to a string, we would just use the str function. And this allows me to convert all of the things in this list to strings. Or I maybe convert is kind of weird because the original number still exists, right? But it allows me to get a list that is the result of stringifying all of these things. And the lambda allows me to do that without defining a new function, right? I can store the lambda with a name if I would like to. Do not think that the lambda is magic that is associated with the fact that it's an argument to a function. I can give it a name. I can do my lambda equals lambda x cubed, right? And that's pretty much the same as if I had defined a cubed function, right? Because now I can do my lambda 10 and get the cube of 10, right? Let's see what the type is. Function. Okay, so allegedly the type of my lambda is function, the same as my other function was, right? So if I do type times 2, which I used def to get, that's also function. So the type produced by lambda is the same as the type produced by def, right? They're both functions. I think that's neat. So the reason that we're covering this is because on the list of things to cover is custom layers with custom activation functions. And one of the easiest ways to do that is to provide a lambda with your new activation function. So, and I don't want to introduce a lot of that material at the same time that I'm introducing lambda. I don't know how many of you have seen lambdas before. I don't know how many of you are going to kind of be utterly confused and confuzzled by what the hell I just did. Some people get completely mind blown the first time they really see functional programming. Please do let me know if this is a bizarre concept to you that I have completely inadequately covered. We can go over this in more depth. Okay, that is it for our Python overview. We will start with some basic theory next week.